Hello friends, in the previous lecture we learned that the basic function of a comparator is to compare the magnitudes of two binary quantities to determine the relationship of those quantities. Then we learned that a decoder is a digital circuit that detects the presence of a specified combination of bits on its inputs and indicates the presence of that code by a specified output level. In today's discussion, we shall be talking about encoders, multiplexers and demultiplexers. An encoder is a combinational logic circuit that essentially performs a reverse decoder function. An encoder accepts an active level on one of its inputs representing a digit such as a decimal or octal digit and converts it to a coded output such as BCD or binary. Encoders can also be devised to encode various symbols and alphabetic characters. The process of converting from familiar symbols or numbers to a coded format is called encoding. The decimal to BCD encoder. This type of encoder has 10 inputs, one for each decimal digit and 4 outputs corresponding to the BCD code as shown. This is a basic 10-line to 4-line encoder. The BCD code is listed in this table. From this table, you can determine the relationship between each BCD bit and the decimal digits in order to analyze the logic. For instance, the most significant bit of the BCD code A3 is always a 1 for a decimal digit 8 or 9. An OR expression for bit A3 in terms of decimal digits can therefore be written as A3 is equal to 8 plus 9. Bit A2 is always a 1 for a decimal digit 4, 5, 6 or 7 and can be expressed as an OR function as A2 is equal to 4 plus 5 plus 6 plus 7. Bit A1 is always a 1 for a decimal digit 2, 3, 6 or 7 and can be expressed as A1 is equal to 2 plus 3 plus 6 plus 7. Finally, A0 is always a 1 for a decimal digit 1, 3, 5, 7 or 9. The expression for A0 is 1 plus 3 plus 5 plus 7 plus 9. Now let us implement the logic circuitry required for encoding each decimal digit to a BCD code by using the logic expression just developed. It is simply a matter of ORing the appropriate decimal digit input lines to form each BCD output. The basic encoder logic resulting from these expressions is shown in the figure. When a high appears on one of the decimal digit input lines, the appropriate levels occur on the 4 BCD output lines. For instance, if the input line 9 is high, assuming all other input lines are low, this condition will produce a high on output A0 and A3 and lows on output A1 and A2, which is the BCD code 1001 for decimal 9. The decimal to BCD priority encoder. This type of encoder performs the same basic encoding function as previously discussed. A priority encoder also offers additional flexibility in that it can be used in applications that require priority detection. The priority function means that the encoder will produce a BCD output corresponding to the highest order decimal digit input that is active and will ignore any other lower order active inputs. For instance, if the 6 and the 3 inputs are both active, the BCD output is 0110, which represents decimal 6. As shown in figure, the 74LS148 is a priority encoder that has 8 active low inputs and 3 active low binary outputs. This device can be used for converting octal inputs to a 3-bit binary code. To enable this device, the E1 called the enable input must be low. It also has the EO or the enable output and GS output for expansion purposes. The enable output is low when the enable input is low and none of the inputs 0 through 7 is active. GS is low when enable input is low and any of the inputs is active. As shown in figure, the 74LS148 can be expanded to a 16 line to 4 line encoder by connecting the enable out of the higher order encoder to the enable input of the lower order encoder and negative ORing the corresponding binary outputs. The enable output is used as the 4th and most significant bit. This particular configuration produces active high outputs for the 4-bit binary number. An application. A classic application example is a keyboard encoder. The 10 decimal digits on the keyboard of a computer, for example, must be encoded for processing by the logic circuitry. When one of the keys is pressed, the decimal digit is encoded to the corresponding BCD code. This figure here shows a simple keyboard encoder arrangement using a 74HC147 priority encoder. The keys are represented by 10 push button switches, each with a pull-up resistor 2 plus V. The pull-up resistor ensures that the line is high when a key is not depressed. When a key is depressed, the line is connected to ground and a low is applied to the corresponding encoder input. The 0 key is not connected because the BCD output represents 0 when none of the other keys is depressed. The BCD complement output of the encoder goes into a storage device and each successive BCD code is stored until the entire number has been entered. Methods of storing BCD numbers and binary data are covered in later lectures. Multiplexers. A multiplexer is a device that allows digital information from several sources to be routed onto a single line for transmission over that line to a common destination. The basic multiplexer has several data input lines and a single output line. It also has data select inputs which permit digital data on any one of the inputs to be switched to the output line. Multiplexers are also known as data selectors. A logic symbol for a 4-input multiplexer is shown in figure. Notice that there are 2 data select lines because with 2 select bits, any one of the 4 data input lines can be selected. A 2-bit code on the data select input will allow the data on the selected data input to pass through to the data output. If a binary 0, that is S1 is equal to 0 and S0 is equal to 0 is applied to the data select lines, the data on the input D0 appears on the data output line. If a binary 1, that is S1 is equal to 0 and S0 is equal to 1 is applied to the data select lines, the data on the input D1 appears on the data output. If a binary 2, that is S1 is equal to 1 and S0 is equal to 0 is applied, the data on D2 appears on the output. If a binary 3, that is S1 is equal to 1 and S0 is equal to 1 is applied, the data on D3 are switched to the output line. A summary of this operation is given in this table. The logic circuitry required to perform this multiplexing operation is as shown here. The data output is equal to the state of the selected data input. You can therefore derive logic expression for the output in terms of the data input and the select inputs. The data output is equal to D0 only if S1 is equal to 0 and S0 is equal to 0 and Y becomes D0 S1 bar S0 bar. The data output is equal to D1 only if S1 is equal to 0 and S0 is equal to 1 and the output becomes D1 S1 bar S0. The data output is equal to D2 only if S1 is equal to 1 and S0 is equal to 0. Therefore, the Y output becomes D2 S1 bar S0. The data output is equal to D3 only if S1 is equal to 1 and S0 is equal to 1 and Y is equal to D3 S1 S0. When these terms are ORed, the total expression for the data output is like this. The implementation of this equation requires 4 3-input AND gates, a 4-input OR gate and 2 inverters to generate the complements of S1 and S0. Because data can be selected from any one of the input lines, this circuit is also referred to as data selector. The 74HC157 quad 2-input multiplexer. The pin diagram and logic symbol for the 74HC157 is shown here. It consists of 4 separate 2-input multiplexers. Each of the 4 multiplexers shares a common data select line and a common enable. Because there are only 2 inputs to be selected in each multiplexer, a single data select input is sufficient. A low on the enable input allows the selected input data to pass through to the output. A high on the enable input prevents data from going through to the output, that is, it disables the multiplexers. Notice that the 4 multiplexers are indicated by a partitioned outline and that the inputs common to all 4 multiplexers are indicated as inputs to the notched block at the top, which is called the common control block. All labels within the upper multiplexer block apply to the other blocks below it. Notice the 1 and the 1 bar labels in the multiplexer blocks and the G1 label in the common control block. These labels are example of the dependency notion system specified in the IEEE standards. In this case, G1 indicates an AND relationship between the data select input and the data input with 1 or 1 bar labels. In other words, when the data select input is high, the B inputs of the multiplexers are selected, and when the data select input is low, the A inputs are selected. A G is always used to denote AND dependency. Application: a 7-segment display multiplexer. Figure shows a simplified method of multiplexing BCD numbers to a 7-segment display. In this example, a 2-digit numbers are displayed on the 7-segment readout by the use of a single BCD to 7-segment decoder. The basic method of display multiplexing can be extended to displays with any number of digits. The basic operation involves the application of 2 BCD digits to the multiplexer inputs. A square wave is applied to the data select line, and when it is low, the A bits are passed to the inputs of 74LS47 BCD to 7-segment decoder. The low on the data select also puts a low on the A1 input of the 74LS1392 2-line to 4-line decoder, thus activating its 0 output and enabling the A digit display by effectively connecting its common terminal to ground. The A digit is now on and the B digit is off. When the data select line goes high, the B bits are passed through to the input of the BCD to 7-segment decoder. Also, the 74LS139 decoder's 1 output is activated, thus enabling the B digit display. The B digit is now on and the A digit is off. The cycle repeats at the frequency of the data select square wave. This frequency must be high enough, about 30 Hz, to prevent visual flicker as the digital displays are multiplexed. Demultiplexers. A demultiplexer basically reverses the multiplexing function. It takes digital information from one line and distributes it to a given number of output lines. For this reason, the demultiplexer is also known as a data distributor, and you will learn that decoders can also be used as demultiplexers. Figure here shows a 1-line to 4-line demultiplexer circuit. The data input line goes to all of the AND gates. The 2 data select lines enable only one gate at a time, and the data appearing on the data input line will pass through the selected gate to the associated data output line. We have already discussed the 74HC154 decoder in its application as a 4-line to 16-line decoder in previous lecture. This device and other decoders can also be used in demultiplexing applications. The logic symbol for this device when used as a demultiplexer is shown in here. In demultiplexer applications, the input lines are used as the data select lines. One of the chip select inputs is used as a data input line, with the other chip select input held low to enable the internal negative AND gate. This device may be available in other CMOS or TTL families. One of the chip select inputs is used as a data input line, with the other chip select input held low to enable the internal negative AND gate. This device may be available in other CMOS or TTL families. So friends, that brings us to the end of our discussion in this lecture, and therefore we sum up. In this lecture, we learned that an encoder accepts an active level on one of its inputs representing a digit such as a decimal or octal digit and converts it to a coded output such as BCD or binary. Encoders can also be devised to encode various symbols and alphabetic characters. The process of converting from familiar symbols or numbers to a coded format is called encoding. A multiplexer is a device that allows digital information from several sources to be routed onto a single line for transmission over that line to a common destination. The basic multiplexer has several data input lines and a single output line. It also has data select inputs which permit digital data on any one of the inputs to be switched to the output line. Multiplexers are also known as data selectors. A demultiplexer basically reverses the multiplexing function. It takes digital information from one line and distributes it to given number of output lines. So that is it for today. See you in the next lecture with more on logic circuits. Thank you very much.